We'll conclude our discussion of function theory with the notion of inverse function. Intuitively, this is just a function that undoes a function f of x. So given a function f of x, we want to compute the function that undoes it. This is the inverse function. The notation for it is straightforward. We use f and then put a -1 in the superscript of f. So this is just the notation. Now, mathematically, what is this doing? Well, if I want to undo my function f, this says that given an input x, if I first apply f to get f of x, and then apply f inverse, I ought to recover what I started with. So if I compose f and f inverse, then I ought to get the identity function. I ought to get something that sends every input back to itself. So that's this picture here. F composed with f inverse of x is x, and then we also set f inverse composed with f of x is x. So the picture is like this. I start with some input x. I get f of x by applying the function f, and then I apply the function f inverse to get back to x. So an important thing to understand is that not all functions have inverses. There's a simple check you can do, sort of in the spirit of the vertical line test, that will tell you, given the plot of a function, whether or not it has an inverse function. A bit about notation, which is a little deceptive. The notation for f inverse is not the same as raising the whole function to the -1 power. Right? So just to recall, if I have any quantity and I raise it to the -1 power, this is 1 over that. What we do with the inverse function is not that. The inverse function is the function that undoes f according to composition. It is not the same as saying 1 over f. Okay, so a cute comment that can be really useful for the CLEP are these. If I have a function with a domain and range, the inverse function has the same domain and range but switched. So the domain of f is the range of f inverse, and the range of f is the domain of f inverse. So what about this check to determine inverse functions? So recall that we can check if a function if a mathematical relationship is a function via the vertical line test. So I take a plot of the mathematical relationship and then draw vertical lines. As long as these lines only intersect the function one time, it's a function. Now, to check if a function has an inverse function, I do what's called the horizontal line test. So I draw horizontal lines, and I ask the question, is it the case that every horizontal line intersects the function at most one time? If it does, then it has an inverse. If it doesn't, then it doesn't. So here's a picture of an affirmative case on the left. So the function is y equals x cubed plus 3x minus 2. And I plotted it. So I draw horizontal lines. All of these intersect the function only once, and hence I have an inverse function. Compare that to the plot for y equals x squared minus 1. This is a function. It passes the vertical line test. But almost every horizontal line that intersects the function intersects it at 2 points. So in fact, there's no inverse function on here. So look at these sort of intersections that are not singular. So this fails the horizontal line test. So how does one compute an inverse function? Well, the easiest way to do it is, given the formula y equals f of x, switch the roles of y and x, and then solve for y. So let's look at some examples. For each of these, we want to plot the function, determine if it has an inverse function using the horizontal line test, and if it does have an inverse function, compute it using the rule I just gave. So let's start with f of x equals x squared. So we should know how to plot this at this point. So something like this. And I ask myself, is it the case that every horizontal line intersects this function at most at one place? So no. So this fails the horizontal line test, so not a function, or rather does not have an inverse function. So let's look at now f of x equals x cubed. So we know from earlier work what this looks like. Okay. And now I run the horizontal line test. So I start drawing some. And it appears that they all intersect the function only once. So this passes the horizontal line test. Great, so I know an inverse exists. Now, as is often the case in mathematics, knowing that something exists is not the same as actually computing it. It's actually getting your hands on it. So for this, we have to switch the roles of x and y here, and then solve for y. So I'll write y equals x cubed, do this switch I was talking about, and say x equals y cubed. And now I solve for y. So I take the cubed root of both sides, and I determine that f inverse of x is the cubed root of x, or x to the 1/3, however you like to write that. So I'm going to plot the inverse function here. Okay. So you can see that the inverse function does bear some geometric similarity to the original function. In fact, it is the same thing if I take the original function and flip it over the line y equals x. We'll get into more of this notion of symmetry in a later module. So let's look now at f of x equals e to the x. So we'll start with plotting. So the plot is something like this. And I'll do the horizontal line test. So it passes the horizontal line test. Each one only intersects once. Okay, so to compute the inverse, I write y of x equals e to the x. So I'll write y equals e to the x. And then I'll switch the roles of x and y. And then my goal is to solve for y. So the question is, what function will isolate y here? What function will undo this exponentiation? Natural logarithm. So natural log of x is equal to y. So we conclude that f inverse of x is equal to natural log of x. Okay, so sort of as before, we see that the logarithm and the exponential function have this visual similarity, again, given by symmetry over the line y equals x. Actually, so how about this function, f of x equals cosine of x? Well, this is a very important function to consider for the CLEP exam. And in fact, it's the first of a new set of functions we're going to examine in the next module. We're going to focus on trigonometric functions. So I'll give you definitions, examples, and we'll, of course, get to inverse trigonometric functions. So this can be sort of thought of as an advertisement for things to come. So if you're not familiar with cosine, that's okay. We're going to spend a whole module studying these objects.